We are going to chat today about properties of the natural logarithmic function. So hopefully um, you remember the properties of logarithms. And again, just in case you haven't done them in a while, we're going to go ahead and review them a bit. And then we're going to see how we can actually use the properties to help make taking derivatives a little easier. Whoa. All right, so let's talk about the properties. Some of the interesting properties of natural log. Now, these properties are not just true for the natural log of x. They are also true for all logarithms, based whatever you want. But natural log we use more than, is one of the more common, well, I shouldn't say common because we have a common logarithm, one of the most used logarithms in mathematics. So just a couple properties. So the first one is if we have the natural log of x times y, and these are in your book. I'm sure you've already looked at these, but it doesn't hurt to see them again. This is what we call the product rule. When I take the natural log of a product, it breaks up into addition. And the whole reason this is true is because remember what the natural logarithm spits out. It spits out exponents, right? It's the exponent to which you would raise e in order to get x, or the exponent in which you would raise e in order to get y. And what do we do with exponents when we multiply things with like bases? We add them. So that is why, that's kind of why. That's not a great explanation, but that's kind of why that's true. So then we also have the natural log. Now I'm going in a little bit of a different order than your book. But the natural log of a quotient is just becomes subtraction because, again, what do we do with exponents when we divide like bases? We subtract them. So that leads us to the natural log of 1 over x, which, if you use this quotient rule from above, what you would get, let's just do a little side work here. You would get the natural log of 1 minus the natural log of x. But let's think about this. What is the natural log of 1? Remember what this is asking. This is asking e to the what equals 1. That's what a logarithm asks. And so what would I raise e to get 1? Well, any number raised to the 0 power is 1. So natural log of 1 is 0. That's something that I think we'll actually add to these properties that they haven't added in. But so I know 0 minus the natural log of x is just a fancy way of saying the negative natural log of x. And then this is the power rule. If I have the natural log of x raised to some number b, that can be any number, we can bring that b down and take the natural log. Now, because you are now a calculus student, this guy's going to give you some trouble. Not trouble necessarily, but bringing this b down is very similar, right, to using the power rule for derivatives. These are different. This is not taking a derivative. This is just saying, you know, if I have the natural log of x cubed, I could write that as 3 natural log of x. This is not a derivative. This is an equality. Natural log of x cubed is equal to 3 natural log of x. And then I just want to add a couple more here that your book didn't add. What is the natural log of 1? We know that that guy is 0. Just a reminder, when I take the natural log of e to the x, those guys cancel out. So whatever I'm raising e to, they will cancel out. Again, what is that asking? What do I raise e to get e to the x? I would raise it to the x power. So these properties are very, very important. You're going to need to know them for the test. I will not explicitly state the product rule or anything, but you need to know how to use them. Okay? So now I'm just going to do a bunch of examples for you, and then we'll talk about this idea of logarithmic differentiation. So let me show you where these are kind of useful. So let's find dy dx. And of course, you're going to have a couple on your assignment that have you just simplifying logarithms. I'll let you do that on your own. But what I would like to focus on is how do we take, use these properties of logarithms to help us take derivatives. That's what we care about, right? We care about derivatives. This is calculus. What do we do in calculus? We take derivatives. I joke with my face-to-face class that when in doubt, the answer should be take the derivative. So let's start off kind of simple here. What if I had the natural log of x e to the x cubed plus 1? So look let's look at this really quick. If you notice, if I were to just take the derivative of this as is, I would do 1 over the stuff, right? 1 over x e to the x cubed plus 1 times the derivative of the stuff. And when I do the derivative of the stuff, I'm going to need to use the product rule. Not that we're scared of using the product rule, not a big deal, right? We don't care. But look at how this could be easier. First off, I'm going to use property 1. Okay, I'll just put a 1 here to show you what I'm going to use. So I'm going to use the product rule. And what does the product rule tell me to do? Oh, come on, I don't need to stay angry. The product rule tells me to break them up using addition. So this becomes the natural log of x plus the natural log of e raised to x cubed plus 1. Okay, and now I have not done any calculus yet here, so I need you to understand that when you're using these properties to break up the natural logarithm, you've not taken the derivative yet. Okay, and so now I'm just going to simplify this a little bit more. This would give me the natural log of x, and then we saw that the e and the natural log cancel out, so this would just be x cubed plus 1. So while that was quite a bit of work, well, not really, we're not scared of hard work, right? It will be useful for us when we take the derivative, because look at how nice this is going to be now. dy dx, what's the derivative of the natural log? It's just 1 over x. What's the derivative of x cubed? That, my friends, is just 3x squared. And we're done. So that was pretty nice that the properties of logarithms gave us a way to find the derivative in an easier way than we might, than we might have to if we were just going to leave it as the natural log. So let's look at another one because those are kind of fun. So let's again find the first derivative, dy dx. Okay, and let's do, I'm going to grab one out of your book here. I think this is one on your suggested. This is number 35. So the natural log of 1 plus x quantity squared times 2 plus x quantity cubed times 3 plus x, oh, isn't that cute, to the 4th. I like the pattern that they did here. All right, so we have 1 plus x squared, 2 plus x cubed, 3 plus x to the 4th. So again, think about what I would have to do with this if I were to take the derivative as is. I would do 1 over all of this crap right here, and then I'd have to multiply by the derivative of this stuff, which you notice we'd have to use the product rule twice because I have 3 things multiplied together. Where instead, if I just use the properties of logarithms, so again, I'm gonna show you each step here, but you can skip some of these steps if you see what it is. If you remember these properties, oh, I need a plus sign in there. I'm just using the product rule to break this guy up. Okay. Now I'm going to use, so I'm just using the product rule. Now I'm going to go back and I'm going to use this guy. Oh, whoops. Doesn't like it when I do that. I'm going to use this guy right here, the power rule. Okay. Whoops. Come on, Sarah. All right, I'm going to use the power rule. Again, I haven't taken any derivatives yet. So I'm going to bring the 2 down, natural log of 1 plus x. I'm going to bring the 3 down, natural log of 2 plus x. And I'm going to bring the 4 down. Because I don't want to do 1 over that and take the derivative of that, right? We want to make our lives as easy as possible. All right, so look at this guy. This is going to be so much easier to take the derivative of. So let me erase a little bit up here. Give us some room. So I don't feel like making a new one. All right, so get rid of that. So what are we going to do now? Let's take dy dx. And again, 1 over the stuff times the derivative of the stuff. So I still have this 2 times 1 over the stuff times the derivative of the stuff, but the derivative of 1 plus x is just 1, plus, and again, I'm showing you every step if you see what this answer is. I forgot my 3, I hear ya. I hear ya. In my head. That should worry you maybe a little bit. All right, so 1 over the stuff times the derivative of the stuff on all this. If you guys can see what the answer is and you want to just simplify it right away, you sure can. And then I'm just going to move my 2's. This is 2 over 1, right? Make sure you don't multiply that 2 on the top and the bottom. That's not how multiplication works with fractions. This is 2 over 1, so I multiply the top by 2 and just the bottom by 1. So I get 2 over 1 plus x plus 3 over 2 plus x. There's some loud people outside my office, so I'm sorry if you hear that. 4 over 3 plus x. And that, my friends, is the derivative. Isn't that great? It helps so much. I just love doing those. I think that's really fun. Whoa, it's a little crazy. But much, much easier than if I were to take 1 over all of this crap and do the derivative of the crap. That should be my new, my new one. Maybe not super professional. All right, so let's look at something. The last thing I want to talk about in this section is called logarithmic differentiation. And I know you've already read the section because you're good calculus students. But I just want to show you a couple of examples of this. Okay, so remember what logarithmic differentiation does is we're going to actually bring in a logarithm into a function that doesn't involve a log, and we're basically just bringing in that logarithm to use its properties. So for example, let's say I had y equals x times the square root of x squared plus 2 times 3 minus x all raised to the 5th power. So if I wanted to take the derivative of this, if you notice, this is going to be a little difficult. Not difficult, we're not scared, but we have the product rule, right? Because we have 3 things. So we're going to have to use the product rule twice. So here's what logarithmic differentiation has you do. It says, okay, well, let's bring a natural log. Now, if you do it to one side, you must, my friends, do it to the other, right? That is like the almighty rule in mathematics. So I'm going to bring in this natural logarithm, and the whole reason I bring this in is so I can split this guy up. So when you originally do this, it's not going to look like it's really helpful, but I promise it is instead of having to take the derivative of this. So I'm going to use my properties of logarithms, so I feel like you feel pretty good about these. So I'm going to, remember this guy right here is all to the 1/2 power. So when I bring the product rule in, I split them up with addition. And then I'm going to bring all of my exponents down. So 5 natural log of 3 minus x. Okay, so here's the great thing about logarithmic differentiation. These guys are going to be much easier to take the derivative of. I'm just going to do 1 over the stuff times the derivative of the stuff, and it should be pretty easy. Now, how we're going to do this, notice, please, 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 notice you don't just have y over here. So we can't just ignore that, right? It's not like, it's your kids and you ignore them. You can't just ignore that. I'm kidding, I don't ignore my kids. We can't just ignore that this is the natural log of y and not just y. So what we need to do is we actually are going to derive implicitly. So I'm going to take d dx of this whole side, and I'm going to take d dx of this side. And I'm being lazy. I should probably rewrite the whole thing, but I'm not going to. All right, so d dx of this side, let's talk about what's happening here. So the derivative with respect to x, my outside function is natural log. So I do 1 over the stuff times the derivative of the stuff. But what is the derivative of y? Well, we don't really know, so we just put dy dx. I need to see this. I need to see your dy dx's so I know what's going on. Now on the right-hand side, notice everything is already in terms of x. There should be like music playing. All of this is in terms of x, so I can just start getting crazy, taking derivatives, having a good time, right? So derivative of natural log of x is 1 over x plus 1/2 times 1 over the stuff times the derivative of the stuff. So the derivative of the stuff can just go ahead and go on top, because when you multiply by 2x over 1, it's just going to go in the numerator. Plus 5 times 1 over the stuff times the derivative of the stuff. Okay, so this is so nice. So I think I'll finish this up and then we'll call it good. Let's see what happens here. So I get 1 over y still times dy dx equals, I'm just going to clean this up a little bit, plus cancel my 2's here. So I get x over x squared plus 2. Don't you dare cancel those x's. You may not do that because of this addition sign. And then I like to bring that minus out. And so this is 5 over 3 minus x. Now, let's think about this. What was my goal? I guess I didn't state that up here anywhere. My goal is to solve for dy dx. I don't know if I told you that, but we're trying to find the derivative. So how do I solve for dy dx? Well, I need to get it by itself. So what I'm going to multiply both sides by is I'm going to multiply both sides by y. Okay? And if you notice, we started with a function that is explicitly described in terms of x. So I want my final answer to be just in terms of x. Ooh, I don't know if I'm going to be able to fit this, but we'll try it. So what's my final answer? Dy dx equals 1 over x plus x over x squared plus 2 minus 5 over 3, I'm not going to be able to fit x, 3 minus x times y. Now what is y? We're going to go all the way back up to here, and we're going to grab y. And I know what your first question is. Sarah, do I need to simplify this? And I say no. Do not simplify this. This is times. Sorry about the space here. Do not simplify this because it's just a practice in taking derivatives. If we wanted to, we could distribute this through, and actually some nice things happen because your denominators cancel out. Well, some of them. So it actually works out pretty nicely because a lot of your denominators will cancel out. So if you want to simplify this, if you can't sleep tonight without simplifying this, you go for it. Go ahead and simplify this. If you don't want to do it, though, this answer right here is sufficient. Okay, I hope that makes sense. If you have any questions about this, I know that remembering these properties can be tricky, so make sure you do the suggested problems. In the homework, basically like 1 through 21 are really good examples of how to use the properties, and you can do any of those, any of the odds. You can check your answer in the back of the book, and if you don't know how they got that answer, hey, just send me a quick email, call me. I miss you guys. You never talk to me. So let me know what I can do to help and have fun.